All right, cool. So welcome back to another session of CE 374U, Urban Stormwater. I've got a couple announcements before we get started. So first, homework 1 grades are posted. So please let us know if you have any, if you found anything in the grading that you weren't sure about that you want to address with us, please do that. If you have any questions on the grading for the entire class, you can go ahead and ask those questions now. Were there any questions on the grading of homework 1 that would benefit the class? Okay, I got a couple of questions about showing units in code. I think that there's two acceptable ways to do that. The first is to reference the units in the variable name. And the second is to reference the units in a comment, like an inline comment. Okay, so those are two acceptable ways to keep track of units within code. Okay, are there any questions? Homework 1 grading? Okay, cool. Well, please let us know if you have any questions or concerns about your individual grades, and we will get on that. Okay. Okay. Second, homework 2 is due next week. Are there any questions on homework 2 that would benefit the class that you'd like to ask now? Any questions on homework 2? Okay, cool. And finally, I posted an announcement on this yesterday, but we will be doing an in-class exercise with ArcGIS next week. The installation procedure for ArcGIS can sometimes be somewhat painful. So I would recommend installing that as soon as possible. So I've posted instructions for how to install ArcGIS in the announcements. Use this link here to access kind of all the information you will need to get ArcGIS set up. So I have specific bullet points here for essentially the different aspects that you'll need to be aware of when you are installing it. Yes, there's a question. So I would recommend updating it so that we're all in the same version so that the instructions will be the same for everybody. So I updated mine from 2.8 to 3.0 last night. To do that, I had to go through a couple extra steps. I think one of the things is you need to install like a .NET runtime or something. So just make sure you take care of all that stuff so that we have the software ready to go for next week. You can use an existing version, but I think the safest thing to do would be to update it. Yeah. So you just follow the same instructions for, yeah, it overwrites your existing installation when you do this. Okay. Okay. Any questions about ArcGIS installation? Okay, so just make sure you do this before class on Tuesday. If you have any issues with installing ArcGIS, come see me and I will help you out, okay? Great. Oh, also note, sometimes there's some confusion about this. If you're off campus, you will need to use UT's VPN to use ArcGIS because you need to connect to the licensed server. So just keep that in mind. If you're off campus, ArcGIS will require you to log in with a VPN so that you're on UT's network. Okay, great. Oh, another quick announcement. There was a job posting in Stormwater, and I posted an announcement about that, but I just want to let you know there is a job opening for a stormwater engineer. So go ahead and apply that and show what you've learned in this class, okay? Okay, great. So let's do a quick recap of what we covered last time. So last time we finished up our discussion on the green amped infiltration model. So up till this point, we spent the last couple of lectures discussing different infiltration models and how to partition rainfall into infiltration and runoff. And then in the second part of class, we introduced the SCS, or Soil Conservation Service method, for computing infiltration and excess precipitation due to rainfall. So we went through the procedures for how to apply the SCS method, how to compute curve numbers based on land cover and soil type data, and how to compute curve numbers based on antecedent soil moisture conditions. And I gave you a quick example at the end of class where you apply the SCS method to determine infiltration and runoff. So what I want to do for the beginning of class today is I'm going to give you an example to work on that is a little bit more complex. And there's going to be two parts to this. So I expect this to take maybe the first 15 to 20 minutes of class. All right, so I'm going to give you a problem to work on in your groups, and you're going to need to use the Austin Drainage Criteria Manual. So if you have your laptops, go ahead and use your laptops. I'll also post the Austin DCM curve numbers up on the screen. They might be kind of hard to read. Okay, so let's go through the following example. I'm going to have you use the SCS method to determine the excess precipitation. After you complete this, I will give you a little bit of an extra conceptual test to work on, okay? So let's say we have an urban watershed. And it has the following characteristics. Okay, it has the following land cover breakdown. So 30% of the watershed area is open space in fair condition. And this has soil group B. Right, we have 50% of the watershed is open space in poor condition. And this is soil group C. And we have that 20% is paved parking lots, roofs, and driveways. Okay, and this is soil group C. Okay, assume that soil moisture condition 3 applies. So I'm going to say assume that AMC3 applies. Okay, so I want you to determine the total inches of runoff or excess precipitation resulting from 2 inches of rain. Okay, and so you're going to need to use the Austin DCM to get the curve numbers. And I want you to determine the excess precipitation, assuming that AMC3 applies. And I will let you work on this for about 5 to 10-ish minutes. And during that time, Becky, would you be able to maybe walk around and just, see how everybody's doing? Okay, cool. All right. Are there any solutions that you'd like to volunteer? Any solutions? Okay, I got a hand here.
0.296 inches.
0.296 inches. I'm getting something a bit different from that. Are there any other answers?
1.24 inches.
Okay, 1.24 inches. Okay, cool. So I'm going to go ahead and reveal the answer. Okay, so, oh, yes. So from that equation, we have that P is equal to PE plus FA plus IA. So that will add up to the original rainfall inches. I don't know if there's a direct there is a relationship between S and P. It's just, I would have to think about it. Okay, so as before, we computed the composite curve number, essentially computing the areal weighted average curve number based on these land cover types. So if you looked up from the Austin DCM, you got these curve numbers of 69, 86, and 98. So we scaled them by their respective percent areas for this catchment to get a curve number estimate of about 83.3 for our composite curve number. So after computing the composite curve number, we apply the soil moisture adjustment to convert it to AMC3 conditions. So these are the high antecedent soil moisture wetness conditions, and that gives us an adjusted curve number of 92. Okay, so note that in the notes, I didn't say what order to do these in. So this is the order you want to use for your homework. Okay, so you compute the composite first, then you adjust it. Okay. Right, and it's just because of the way that these are defined in the SCS method. Okay, so next we used the curve number equation to compute our storage, our maximum possible storage S. Our maximum possible storage is 0.8719 using the curve number we obtained before. And finally, with that, we can compute the excess precipitation. So plugging in our value for S into our equation for the excess precipitation, we get about 1.24 inches of runoff that occur for 2 inches of rainfall. Okay, and note, as some of you pointed out, this equation for S is in inches. So this wouldn't necessarily give you the same answer if you were using a different unit system. SCS method is a method that was developed in the United States, mostly used in the United States. So uses units of inches here. Okay, cool. So I'm going to give you another part to this question to test your conceptual knowledge of the curve number method. Okay, so let's say we have the same scenario, but now assume that we have a rainfall event divided up into 3 hours. Okay, so assume 3 hours of rainfall. We have precipitation in the first hour of 2 inches. For the second hour, we have precipitation of 3 inches. And for the third hour, we have precipitation of 1 inch. So note, this indicates the total depth of rainfall that fell within that hour. Okay, so what I want you to do is compute the excess precipitation for each hour. Okay, so what is the excess precipitation that occurred within each hour? Okay, so this question or this exercise kind of reveals an important point about the curve number method. Okay, so I want you to compute the excess precipitation for each hour, which I will call delta PE1, delta PE2, and delta PE3. Okay, so I'll give you about 5 or so minutes to work on that. All right, everybody. I think I see some answers. Okay. So I'm going to go ahead and reveal the answers to you. So these are who got these answers here? Let's just see a show of hands. So this reveals an important point about the curve number method. What is when we have this expression for the precipitation that occurs in the curve number method, what precipitation is that? For our equation here, what is this P actually? It's the cumulative rainfall. Okay, so if you have a storm event that has multiple parts to it, the value of P that goes into this equation here is the cumulative rainfall up to that point in time. Okay. So what's another thing that this implies about the curve number method? What does it imply about the amount that infiltrates over time? So the curve number method, when you're simulating excess precipitation using the curve number, basically the available space in your soil volume only decreases over time, okay? Because you're adding more rainfall in and it doesn't have any way to get out. So the infiltration capacity of your soil essentially always decreases over time. So another important fact to remember about the curve number method is it's not suitable for continuous simulation. It's only suitable for simulating a single rainfall event. Okay, but essentially this is the solution procedure. So for computing the excess precipitation that occurs within the first hour, we can simply use the answer we got from the last part of the problem. This is the excess precipitation response with respect to 2 inches of rainfall. For the second time period, we use the cumulative precipitation that occurred within the first 2 hours, which is 2 plus 3 = 5. We plug that into our curve number, our SCS method equation. We get that 4.09 inches of excess precipitation occurred over the first 2 hours. And then to compute the excess precipitation that occurred in the second hour, we simply take the excess precipitation within the first 2 hours and subtract the excess precipitation within the first hour. Similarly, for the entire 3 hours, we plug in the entire cumulative rainfall over the 3 hours and subtract the excess precipitation from the first 2 hours. Okay, so keep this in mind when you're using the SCS method. It uses the cumulative precipitation over a storm event. Okay, and that implies that it's also not suitable for continuous simulation. Okay, so it has to be reset after every storm event. Okay, are there any questions on the curve number method? Great. Okay, so let's do a quick recap. Okay, so let's recap where we are. So today is going to be our final lesson on hydrology for stormwater. Okay, let's recap what we've covered so far within this module. And we're going to take a look at our hydrologic cycle in an urban watershed again. Okay, so we have our water cycle. We have a water table here. And let's just label the different parts of the water cycle that we've talked about. So in the channel, we have channelized flow. This is what we talked about in the first part of the class. We have precipitation that falls over the catchment. Okay, so we talked about this. And what methods did we use to analyze the amount of precipitation that could occur in an urban watershed? Yeah. IDF curves. What's the other technique we also talked about? Related to IDF curves. We also talked about the alternating block method. Okay, so we discussed how we could estimate the amount of precipitation that occurs using IDF curves and the alternating block method. Okay, the next thing we talked about was basically the two major parts of the hydrologic cycle we're interested in with respect to stormwater. How much water infiltrates and how much water doesn't infiltrate. Right? So what methods do we use to analyze these two quantities? Someone, anyone want to volunteer an answer? Yes.
Infiltration excess, saturation excess.
Right, so we talked about infiltration excess runoff, saturation excess runoff. What are some methods we use to compute the amount that infiltrates and the amount that runs off? Yes.
Green amp.
Green amp is one of them. And the other one that we talked about is SCS method. Okay, cool. Just doing a quick recap of everything we've learned in the hydrology module. Okay, so we covered precipitation. we covered infiltration, we covered channelized flow. There's one part we haven't addressed yet. Okay, which is overland flow. Okay, so when we're talking about rainfall runoff modeling, we need to understand, first what volume of runoff we get. So that we obtain from green amped or from the SCS method, but we still need to understand how it routes into the channel network. Okay. So that's what I'm going to be talking about for the next section of the lecture. We're going to particularly be talking about the unit hydrograph approach. Has anyone heard of the term unit hydrograph before? Okay, that's good enough. Okay. Did anyone who take hydrology talk about unit hydrographs? Okay, you talked about unit hydrographs and hydrology? Okay, cool. So we're going to be talking a bit about unit hydrographs in this class and how we can use it to essentially understand the time dynamics of this overland flow, how much water is arriving at the channel at any point in time. Okay, so let's talk about how to compute or how to model overland flow. There's really two ways that this is done. Okay. And the first method is to use physically based models. Okay, and generally what's used in stormwater would be the kinematic wave model. Okay, who remembers kinematic wave from all the way back in the beginning of class? Okay, so it turns out that that simplification of the full equations for unsteady flow works very well for overland flow. Okay, so you find that many models use kinematic wave to model the overland flow portion. So you can model it as a wide rectangular channel, apply the kinematic wave. And what you're doing on the homework for problem 2 is essentially this process. Okay, you are routing the flow you obtain from the green amped model into a channel using essentially a simplified form of the kinematic wave equation. Okay, so that's one way to do it. But oftentimes, this isn't necessarily the ideal method. It requires a lot of data. It's computationally intensive. And often if you're just using a single wide rectangular channel, it doesn't handle complex terrain. So as we mentioned before, water has to travel through various complex paths to reach the ultimate channels downstream. And so a physically based model like this often isn't really able to model those complex paths. Okay, so the other major method used to model essentially how excess precipitation transforms into channelized flow is to use what's called a unit hydrograph. Okay, so let me give you the basic idea of a unit hydrograph. Okay, so let's say we want to model the runoff response to an arbitrary rainfall input. Okay, so let's say we have our plot of rainfall here. Let's just say it's PE, our excess precipitation. Maybe it looks something like this. We got, from our alternating block method, we have a very sharp peak in the middle. That's what our rainfall looks like. And we have some watershed. Okay, the rainfall is falling over this watershed. For now, we're just going to assume it falls uniformly over the watershed. And we get some response at the outlet. So I will label in red. Let's say that this is the outlet to a channelized section. Okay, so maybe this is just a land service. Maybe there's no real channels here. And our response will look something like this. So it'll take our rainfall event and kind of smooth it out. So we want to model the runoff response from a watershed to some arbitrary rainfall input. That's our ultimate goal. Okay. So why does the watershed smooth out the rainfall response like this? We talked about it a little bit a couple lectures ago. Yep. Exactly, yeah. So as I mentioned a couple lectures ago, let's say we have a watershed. Okay. I'm just going to draw some channels in here, but there don't need to be channels necessarily. And you have rainfall falling over the watershed. And remember, we showed that you could think of this watershed. We look at the outflow response. Okay, if we look at the hydrograph, you'll end up with something that looks like this because the watershed has some distribution of travel times, right? So if water falls over a watershed, so let's say you have an instantaneous pulse of rainfall that just drops over the watershed all at once. Okay, so let's say you just take a giant bucket and throw it over your watershed and it hits uniformly over the watershed all at once. That water has to route through the watershed. So it follows all of these individual paths. And what you get is a shape at the outlet that looks like essentially the travel time distribution of the drops as they fall within the watershed. Okay. So these drops, this travel time distribution is equivalent to the response that you would get if you hit your watershed with an instantaneous unit impulse of rainfall. Okay. Consider that you drop a unit of rainfall uniformly over the watershed, and you allow that water, all those droplets, to route to the outlet. That's equivalent to the travel time distribution of your watershed. Okay. So the idea of a unit hydrograph is as follows. Okay. So one way that we can accomplish our goal of computing the runoff response to an arbitrary rainfall input is to characterize the response of the watershed to a unit impulse of rainfall. Okay, let me just extend this down. Okay, so let's say we have our rainfall hydrograph. Let's just say this is the excess precipitation, this is time. We can characterize the response of the watershed to an instantaneous unit impulse of rainfall. Okay, so this is, you can think of this as maybe 1 inch is maybe the units we're using. Okay, we have rainfall that occurs at an instant in time, and we compute the resulting response of the watershed to that impulse. Okay, so we're dropping rainfall uniformly over the watershed all at once with a unit magnitude. And we can characterize the response to that unit impulse of rainfall at the outlet. And maybe that response will look something like this. Okay. It'll look something like this, maybe. So this is the response of the watershed to a unit impulse of rainfall. It's equivalent to the travel time distribution or approximate travel time distribution within the watershed. Okay, so we compute the response of the watershed to a unit impulse of rainfall, and then we can treat our arbitrary rainfall input as a train of impulses. Okay. So we can treat our real rainfall event that we're interested in as essentially just a sum of different impulse rainfall events at different moments in time. Okay. And all we have to do is add them up together. Okay. And simply add up the resulting responses. Okay. So conceptually, let me just draw a quick drawing here. So let's say we have some rainfall event that looks like this. We have our unit hydrograph. Actually, let me draw this as kind of a discrete series of points here. So we have a rainfall event that might look like this. And our ultimate hydrograph that we're going to end up with is we take this impulse here. We know its response because it's an impulsive rain event. And so we end up with some component of the hydrograph here. We take this part of the rainfall event, we take our unit hydrograph and we scale it by this component and add it on top. Okay, so it will kind of add on top here. And then finally, we take this component here and scale our unit hydrograph by it and add it on top. And we'll end up with kind of maybe a smaller part that's added on, shifted slightly to the right because it occurs later on. Okay, so this is kind of conceptually what's going to happen. Okay. Now there's a big assumption that unit hydrograph theory makes. Does anyone want to guess what that assumption is? What does it assume about the watershed system or the watershed as a system? Yeah. So physically, maybe that might correspond to something like that, but mathematically, there's something that's assuming about the way that the watershed transforms water or transforms precipitation into runoff. Sorry? So that is an assumption that it makes. There's another assumption that it makes. Okay. Any guesses? Okay, so note, this assumes linearity in the watershed response. Okay, in other words, it assumes that the function that transforms the rainfall into runoff is a linear function. That's the only way that you can add up the components together in this way, is if the watershed is a linear reservoir or it behaves as a linear function. How much time do I have here? Okay. Now, let me just kind of give a sense of what I mean by watershed as a linear function. Okay, if we have that, we have some discharge output that is a function of, there's a function of some precipitation input P1, and we have some discharge output to Q2 that's a function of our precipitation input P2, then our function describing the watershed's transformation of rainfall into runoff, if we apply it to alpha Q1 plus beta Q2, it'll give us, it'll give us alpha Q1 plus beta Q2. Sorry, I wrote this wrong. These should be Qs. Okay, and I'll show you a quick example of, sorry, and also this in here, this should be P1 and P2. Okay, so it's a linear function. If we have a rainfall input P1 and a rainfall input P2, and P1 produces discharge Q1, P2 produces discharge Q2, then if we compute the function that gives us our discharge for alpha P1 plus beta P2, it'll simply be equal to alpha Q1 plus beta Q2. Okay. All right. So when is this the case? First of all, are actual watersheds, do you think actual watersheds are actually linear? No, they're not. You can't simply add up the response to a precipitation event on top of another precipitation event because there is nonlinear behavior in the watershed, which we saw in Green Amped and we saw in the way that water was routed. However, we can kind of conceptualize why we can use this approximation. Okay, so one way to think about it is to think about our watershed as if it's a big tank. Okay, so we have a big tank of water. And we have maybe some pipe coming out of the tank. And we have some outflow Q. We have some precipitation falling into the tank. Okay. The tank has a bottom area, let's just call it A. And maybe the height of water in the tank is H. The precipitation we'll call P. Okay, so we can think of the storage in the watershed. Let's just call the storage of water in the watershed S. So this would be the volume of water in the watershed. Okay, and we have that the time rate of change of the storage in the watershed is equal to the inflow minus the outflow. So that's the precipitation minus the discharge out. Okay, and because this is a tank, okay, we can just say that the storage is equal to the bottom area times the height of the water. Okay, so if we substitute that in here, we get A times dHT dt is equal to PT minus QT. And then we can assume that this Q is a linear function of the depth. Okay, so maybe we'll say that it's equal to K times H. Okay, so the outflow is proportional to the height of the water in the tank. Okay, so we'll say that QT is equal to K times H of T. Okay, and thus H of T is equal to 1 over K times QT. Okay, and we can substitute that in and express this entire equation in terms of Q. And what we end up with is A over K times D QT by dt plus QT is equal to PT. Okay, so this is a differential equation with respect to Q, and our input is PT. And essentially what this will get is if you start with some initial water level in the tank, the water level will decrease exponentially over time. Okay, so the outflow is proportional to the depth of water in the tank. And you can think of a watershed, when we're thinking about watersheds as a linear reservoir, this is essentially what you can think of. And you can show that this is linear. Okay, you can show that this is linear. So I'll just quickly go through this. But basically, if we have A over K, so if we have some solution to this differential equation, Q1T by dt plus Q1T is the solution for a given rainfall input P1T. And we have another solution for another rainfall input P2T. And our solution is Q2T. Then you'll find that if you add these two together, okay, this will equal the result of applying this differential equation with P1T plus P2T as your input with Q1T plus Q2T as your solution. Oh, I'm running out of space here. Okay, so this is a linear system. So you find that if you have a solution corresponding to P1 and a solution corresponding to P2, if you add them up together, if you add those two solutions together, it'll be equivalent to plugging in P1 plus P2 as your input to this system, okay? So that's why it is linear, and that's why you can apply this approximation. So we're essentially thinking of our watershed as a big tank where the outflow is proportional to the storage in the tank. That's the major underlying assumption here. Okay. Cool. Are there any questions? I know I went through this fast, but you can verify this yourself by plugging these in. If you're not satisfied by my very quick run through here, okay? Okay. So if we have a watershed that is essentially a linear system, we have a watershed that is a linear reservoir, we can compute the response to any arbitrary rainfall input through an operation called convolution. Okay, who's heard of the term convolution before? Has anyone heard of it? Okay, cool. What context did you hear convolution in?
Like, I know for like, like
That's no, yeah, that's another application where convolution occurs. Do you have any sense for what convolution is in that context?
It's like taking a signal, like a wave, and then like changing it, I guess, in a way. I'm not sure.
Yeah. So I'll give you kind of both a mathematical and conceptual overview of what convolution is. But let me just start by kind of explaining how we're going to use it here. If the basin response is linear, then we can compute the discharge so we can compute the discharge, which I'll call Q, corresponding to some arbitrary rainfall input which I will call P, through discrete convolution. And I will show you mathematically what discrete convolution is, and then I'll kind of give you some intuition for it. Okay, so the operation for convolution is as follows. We have that the discharge at time index n is in November is equal to the sum from m as in Mike equals 1 to n as in November times p at time index m as in Mike times u at time index November minus Mike plus 1. Okay. So this gives us the discharge at time index n. So note here, let me define these variables for you. Q is our discharge. So this is maybe the discharge into the channel. P, this is the precipitation. And U is our unit hydrograph. Okay, so let me give you a visual of what's going on. Essentially what this is doing is it's taking our unit hydrograph and it's taking each element of P, so each impulse of rainfall in our train of impulses, it's scaling the unit hydrograph by that precipitation impulse P, and then it's adding them together while sliding over the unit hydrograph. So I'll show you a visual of what it's doing. Okay. So here is a visual of what's happening with convolution. Okay, so let's say we have like this. I'm just going to draw these plots here. I drew these too big, sorry. I want to give you a conceptual understanding of what's happening here. So let's say that this top plot here, this is our precipitation. Okay, and it's going to look something like this. Okay, so we got 3 impulses of rainfall together. Let's call this P1, P2, P3. Okay, and these plots here, these are our unit hydrographs. Okay, so let me draw each one of them here. We have, let's say our unit hydrograph looks like this. Okay, so we have U1, U2, U3, U4, U5, U6, and I'm going to draw the same thing down here. So we have U1, U2, U3, U4, U5, and U6. Yeah, it's the same U's. So we're just sliding it over in time. Okay, and here we have U1, U2, U3, U4, U5, and U6. And so what we're going to do is we're going to look at what the ultimate discharge response looks like. So remember, these here are these are the unit hydrograph. I'm just shifting them over in time. Make a note that this axis here is time. And this here is our precipitation input. Okay. So let's look at how this creates our discharge response. So basically what we're doing with convolution, okay, we take this U here, and we take each of these U's and we scale it by P1. Okay, so we'll end up with something that looks like this. Let's make it a little taller because P1 is kind of big. So each one of these bars is still our unit hydrograph from before. 1, 2, 3, 4, 5, 6. And each of these bars is P1 times U1, P1 times U2, P1 times U3, P1 times U4, P1 times U5, P1 times U6. Okay, so that's the component of our discharge corresponding to the first impulse of rainfall. Okay, so for the next one, we slide U over once in time. We scale it by P2, and then we add it on top of our response here. Okay, so it's a little bit, P2 is a little bit smaller, so I'll draw these a little bit smaller. So we have this one here, 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 and then we have another, maybe smaller. Actually, this will be a little bit smaller. Okay, so this bar here is P2 U1. This bar here is P2 U2. This bar here is P2, U3. This bar here is P2, U4. And this bar here is P2, U5. And this bar here is P2, U6. Okay, and you can kind of see the pattern here. We take this unit hydrograph, we slide it over again, 1 unit in time, and then we scale it by P3. Okay, and so we're going to, this one will be even larger. So we'll end up with something that looks like this. I'm kind of not really going to keep track of scale anymore here, but you will end up with something that looks like this. And again, this is P3, U1, P3, U2, P3, U3, P4, U4, sorry. There's no P4, there's P3, U4, P3, U5, P3, U6. Okay, so this shape here, this is the discharge response. This is the discharge response to our rainfall event P. Okay, so we have 3 discrete impulses of rainfall. Essentially, we take our unit hydrograph, we scale it by each of those impulses, and we add them together while accounting for essentially sliding over our rainfall in time for each increment, okay? Cool. So I'll give you a bit more intuition about this shortly. Are there any questions on this concept before I move on? So the unit hydrograph, it is different from each watershed. Can anyone tell me why? What does the unit hydrograph represent again? What does the unit hydrograph represent? Right. So it's essentially an estimate of the travel time distribution. So that will depend on the size of the watershed and how the terrain is laid out, essentially. Yeah. Okay. Cool. So I got a little bit of time. So let me give you kind of another example of convolution and how you can think about it. I'm going to need to extend the homework to Thursday. So because I didn't get to the SCS unit hydrograph. So just to let you know, I didn't get through everything, so I will extend the homework till Thursday, okay? Okay, cool. So let me give you, but I think it's important to help you understand this concept because unit hydrograph is really fundamental in hydrology and in stormwater design, okay? Okay, so you can essentially think of convolution is a fancy moving average. Okay, so you can think of convolution as essentially being a generalization of a moving average. We're essentially taking the moving average of a function with respect to another function. Okay, so we're using one function to scale each element of our function. Okay, so let me draw out an example of what I mean here, and we're going to show when convolution is actually equal to a moving average. Okay. Okay, so let's say we have some function here, which I will call P. And we have another function here, which I will call U. And let's say that P, we have time indices 1, 2, 3. For U, we have time indices 1, 2, 3. Okay, and our P function, I'll just draw these axes out. Our P function, I'm going to invert the colors here. Okay, it's going to be 3 at time index 1, 1 at time index 2, and 2 at time index 3. Okay, and for our function u, it's going to have a constant value of 1/3. Okay, let's just write 2/3 1. And it's going to have a constant value of 1/3. Okay, so when you apply convolution with a constant function like this as one of your functions, what you end up with will be actually the moving average. Okay, so let's write down, give me 5 more minutes. And I'm going to show you how we can use convolution. This is the same procedure you'll use on the homework. So I think it will behoove you to follow along here. Okay, so from our function for discrete convolution, we have that the discharge at time index n is equal to the sum from m equals 1 to n of pm u n minus m plus 1. Okay, so let's compute the q at each time index using this formula. This is the same procedure you'll use on your homework. Okay, so for q1, if we follow the formula, essentially what we're going to be doing is as follows. We're going to take our precipitation okay, so this is P1, P2, P3. We're going to take our function ut, which could be our unit hydrograph, and we're going to flip it around. So this is now u1, u2, u3. And we're going to slide this u function over our p function and compute the weighted sum as we slide it along. And you'll see in a second what it's going to do, okay? Okay, and I know I'm almost out of time here. Okay, so for q1, if we apply our function, what we'll end up with is p1 u1 is equal to 3 times 1/3. Should be equal to 1. Okay, so what we've done here is we took our original function. We have our u here. And we slid u over the p function. Okay, so we took this here, we slid u over by 1 so that u1 and p1 are overlapping. Okay, so this is u1, p1. Okay. For the next time increment, q2, we take this and slide it over again. And so what we end up with is we now have 2 bars that are overlapping. Okay, so this is now u2 p1, and this one here is, let me just make sure I have this right here in my labels. This one here is p2 u1. Okay, so our discharge at time index 2 is equal to p2 u1 plus p1 u2. And this is equal to 1 times 1 divided by 3 plus 3 times 1/3. And this is equal to 4/3. Okay. And I'm about out of time. Let me just do one more to make it clear, and I will continue where I left off. Actually, you know what? I'll finish where I left off on Tuesday, okay? Okay.